So in this lecture, we will cover the module 9, that is optimal extraction of renewable and non-renewable resources. So we will learn about natural resources economics and dynamic optimization. So natural resources are the naturally occurring resources which can be made available for mankind under feasible social, economic, and technological framework. So what does this three criteria means? It is social, economic, and technology, right? So social means, let's take an example of drinking water, which is derived from seawater. So can we call this a resource? So first, it have to be socially accepted. That is, that society should perceive that after desalinating seawater, it is safe for drinking purpose. Second one is technology. So there should be available technology for desalination purpose. Third one is economic. So it should be economically feasible uh, or it should be cost effective, right? Now we will try to learn the renewable resources in depth. Not only naturally occurring resources can be termed as renewable resources. Why? Because for any kind of resource from environment, it will be renewable only when it have regenerating capacity within the economically feasible time horizon. So if any kind of naturally occurring resources, that is resource which we derived from economy, it can be termed as renewable when it gets regenerated within a specific time horizon. And opposite to it, if the naturally occurring resources do not have regenerating capacity, then we call them non-renewable resources. The example can be coal, oil. So the coal regenerated itself, but after 100 years, after 200 years or more, it takes to regenerate. So this kind of resources can be termed as non-renewable resources. So now we come to a question which says, does renewable resource also get exhausted? So the answer is yes. Renewable resource may get exhausted if the rate of extraction is more than rate of growth. So let's take an example of um, forest land, right? So if the forest before growing itself or before giving time to replenish itself, if we try to extract the resources from forest, then the regenerating capacity will end for the forest. So in this case, when rate of extraction is very much more than rate of growth, then in the naturally occurring resources, which is renewable also, may get exhausted. Now we will come to the second reason, that is because of human activity or anthropogenic activities, due to which there is change in the climatic condition, because of which the exhaustion of various renewable resources may happen. So this is best suited for various species of animals. So because of change in climate, because of pollution, or because of hot weather, there is extinction of various species of animals, right? So this is one of the example of a case where a natural resource also get exhausted. Now the next part of the question is, are we extracting the natural resources too rapidly or too slowly? So how are we supposed to do? So the economy says optimum rate of extraction should be there. it should not be too rapidly or too slowly. So the rate of extraction should be such that it maximize the intertemporal benefit derived from non-renewable resources, and and also it also maximizes the lifetime utility derived from non-renewable resources. So in this case, since we are talking about the maximization of intertemporal benefit over the horizon of time, or lifetime utility, which is derived from non-renewable resources, in this case, we are not using static optimization, in which the objective is minimized at a specific time period or at only one time period, right? So in the dynamic optimization, at each point of time, we decide the optimality. So in this case, since the optimum rate of extraction is temporal dependent, we will use dynamic optimization to find the optimum rate of extraction. Okay, so the set of natural resources is not closed, rather it is open. So how we decide the open or closed set of natural resources? So it means that the new element can be added to existing set of natural resources. Also, many a times, new some elements can be eliminated, right? Or may get exhausted. So therefore, we say that the natural resources set is not closed, rather it is a open set where addition as well as elimination happens. Now we will learn about the optimal path of extraction of non-renewable resources. So, for any ordinary good, the price is given by marginal cost of production, that is P is equals to MC. So now the question is, can we apply this price principle to the non-renewable resources? So the answer is no, because non-renewable resources are not easily replicable, and since you are using certain non-renewable resources at current, there is some opportunity cost which needs to be incurred, because same resources are not is not available for use of tomorrow, right? So um, let's take an example of price versus marginal. Let's take an example of ordinary good and its price. So let's say that the marginal cost of production is given by MC. Then since there is MUC, which is marginal user cost, which is associated with the usage of non-renewable resources, we increase the total cost as AMC, which is known as augmented marginal cost, which is the sum of marginal cost and marginal user cost, where PT is price of good at time T and YT is some ordinary good quantity. So this graph the give us the difference between the ordinary good and non-renewable resources. Since non-renewable resources are which you are using right now is also having some opportunity cost, so therefore the augmented marginal cost is obtained, which is the sum of marginal cost and marginal user cost. Now we will learn about the optimal path of extraction of non-renewable resources. So it is same as previous. So let's take an example that we have a period only two, that is 0th period and first. This is my time. Now the price of resource at T0 will be P0, and T1 will be P1. Now the resource owner have to decide whether to use the resource today or to use the resource tomorrow. So if I use the resource today, then my benefit will be P0 minus marginal cost of extraction. And if I use at time T1, then it will be P1 minus marginal cost of extraction. Okay, so now since this P1 minus marginal cost of extraction is at time T, we have to derive the present value of this value. So when we derive the present value of the benefit, then what we will do is we will divide it by 1 plus our term, since our time value is 1. So this is the present value of benefit. Now the condition that whether I will use it today or use it tomorrow will be that when the present benefit is more than the future benefit, then I will use today, and when the present benefit is less than future benefit, then I will leave the resource so that I can use it tomorrow. And if these two terms are equal, then we can say that the resource owner is indifferent between the today's and tomorrow's use. So in this case, we can call this a equilibrium condition. Now, from this term, we derive the value of P0, which will be equal to MCE minus P1 into MCE times, this will be multiplication, sorry, this will be same, MCE, we take it to the right hand side, so it will be MCE plus P1 minus MCE plus this. So this whole term is known as augmented marginal cost term, right? So this is known as first rule of optimal extraction of exhaustible resources. So from this two term, this whole term is the term which represents the marginal user cost or opportunity cost of using renewable resources right now. Right. Now, if I have to draw the value of P1, then I will multiply this term to the right hand side, right? So it will be MCE times 1 plus R and P0 times 1 plus R, and then this MCE comes here. So now we derive the value of, from here we have derived the value of P1. So now after that, if we have to find for like if we generalize for PT, then we will say that MCE plus P0 minus MCE 1 plus R to the power T. Since in this case we are taking time as 1, therefore it is 1, and for present value of, let's say, quantity, let's say value A, then it will be 1 plus R to the power T, right? So this T comes as here. So now we have got the general expression of price path for optimal extraction, right? So now we found PT, which will give us the optimum path that decides the price at time T, right? So now from here, when we subtract P1 minus MCE and then divide these, and then we derive the value of R. So R is my discount rate or rate of interest. So this R represents the growth of marginal resource rent. So we say that resource rent is given by P1 minus MCE, right? So this term minus this term divided by this term, right? So this will give us the growth. So the growth of marginal resource rent can be termed as um, the R value, and the resource rent is difference between price and marginal cost of extraction, as we have learned in the previous lectures, right? So now what the Hotelling rules tell us. So the most socially and economically profitable extraction path of non-renewable resources is the one along which the marginal resource rent must grow at the rate of interest or discount. So this rule tells us that the profitable extraction will be there only when the marginal resource rent, the growth of marginal resource rent is at the rate of interest. So let's take an example that if you have 1 rupees today, then the value of 1 rupee will be uh, it is equivalent to 1 plus r, right? So now let's say that in the time at time 1 and at time 0, let's say you have 1 rupees, and at time t you will have, at time 1 t is equals to 1, you will have 1 plus r. So let's say that your rent is P0 minus MCE, then this whole term will be equal to P0 minus MCE times 1 plus R, where R is my discount rate, right? Discount rate as well as interest rate. So now quartering rule tell us that the optimal extraction, like of the path for optimal extraction of non-renewable resources will be equal only when the future value of extraction at time 0, the discounted future value of extraction at time 0 is equal to the uh, extraction of non-renewable resources at time 1. So these are the benefit, right? So this term will be negative. So now what this say tell us is that, let's say that P0 minus MCE times 1 plus R is your future value of benefit, and we use the resource at time t is equals to 0. Now if we have extracted the resource at future only, P1 minus MCE, then this is a future only, t is equals to 1, then this will be my benefit. So the optimal extraction will happen only when these two terms are equal, right? So now Hotelling rule tells us that the profitable extraction path will be where the growth is equal to rate of interest, right? So now this will depend on two factors. The first one is that resource owner will use expected price P1 for the future time, that is T1, right? So price for the resource in future is not known. So we are assuming certain price and then calculating. So the price is assumed value, expected value of price. Now we will the second one is that the rate of interest or rate of discount is not known because it will depend on the resource owner, or it will depend from person to person, right? So if a person is present bias, then it will give more importance to the usage of resource at current time is equals to 0. And if a person is future bias, then uh, it will try to use the resource in future. So those person having present bias will have heavy discount rate, so they will try to extract the resource as much as possible at time t is equals to 0, or initially. So these are the two factors on which the rate of extraction will be dependent. Now let's say that so in summary, what we have derived right now is that we have derived the expression for PT, which is function of marginal cost of extraction and resource rent times the discount rate, right? So 1 plus R, that is R is our discount rate to the power T, where T is our time, right? So optimal path of extraction, when we do, then we decide price at each of the time t. Then as t tends to infinite, we get that pt tends to infinite, since the term 1 plus r to the power t is there, and t tends to infinity, right? So now this means that after sufficient long amount of time, price of non-renewable resources will become infinite. So the question is, will it really become infinite after certain time t, when t tends to t is very large? So the does pt would become infinite as t tends to infinity? So the answer is that PT would never become infinite because of following reasons. So the first reason is price is always determined by demand. So let's say that T is our 200 years, then after 200 years, demand for coal or oil, let's say, would be such that PT will never become infinite. When price increases, the demand will reduce. So in the previous case, we have only assumed the supply condition. We have not considered the demand condition. So when we consider the demand, then the PT will not become infinity. The second one is that when the price increases up to certain level, or when the renewable resources are getting exhausted, then there will be alternative or substitute goods and resources that will be available in the market. So the availability of alternative or substitute goods and resources, or it might be technology, which makes utilization of existing resources more efficient, can be termed as backstop. So the example of backstop can be solar energy, wind energy, nuclear energy, and so on. So because of increased efficiency due to efficient technology or for better efficiency, and then because of alternative technology options, PT would never become infinite when T tends to infinite. Now the role of backstop in the determination of price path of the existing resource. So now let's say that we have MCB, which is marginal cost of extraction of backstop, and let's say that initially the cost of marginal cost of backstop will be much higher than the marginal cost of extraction of non-renewable resources. But once the backstop is available, it is not getting exhausting so soon, so it will be in plentiful. So additionally, there is no user cost for the backstop, as price is only determined by marginal cost of extraction. So let's say that T is the time at which the stock of non-renewable resources get exhausted. That is the shift date from non-renewable towards the backstop. So we will get this is the marginal cost of extraction, and we have some opportunity cost, after which we get augmented marginal cost, which might be at this. And now we will have the backstop cost, which will be given by this line, and G is the shift from non-renewable renewable resources to the backstop. So now in previous we have derived the value of PT, price, function of marginal cost of extraction, and future value of resource rent to the power T, right? When T is our time. Now time at which the shift happens. So PT is the price path of the existing non-renewable resources at time T. So at T, we will shift to backstop due to the exhaustion of non-renewable resources. Then the price PT is given as MCB, marginal cost of backstop, since there is no opportunity cost, right? Now, from equation 1 and 2, we can say that MCB is equal to MCE plus this term. Okay. So we have derived that MCB is function of MCE plus this term. Now, when we rearrange the terms, we have come to the equation where we have, after which we have derived the value of P0. So P0 is equals to MCE plus MCB times MCE upon 1 plus R to the power T. So this is the price at time T is equal to 0. Now for any time T which is less than T, the price will be given by MCE plus MCB minus MCE divided by 1 plus R to the power T minus T. So that this will be my n time T. So we will do n time minus T, and then we will find the value of this price. Now the marginal cost of extraction of backstop determines the price path of existing resource at time T. So from this equation star, we have seen that the price at time T is dependent on MCB. So marginal cost of extraction for backstop determines the price path for existing resources. Also, marginal cost of backstop sets the upper limit to the price of existing resource. So these are the two main conclusions which we have derived from above analysis. So PT will never become infinite and will depend on demand condition, and it will be also determined by alternative resources. So the main point here is that the backstop will also be a function which will determine the price of existing resources. So when price increase, then if the marginal extraction cost of backstop is very high, then maybe price of renewable resources will be higher. However, if it is lesser, then the price of existing resources will not be that high. Additionally, we can say that the marginal cost of extraction of backstop will determine the upper limit on the price of existing resource at time period t. So this MCD will be the maximum price of the renewable resource, of the non-renewable resource. Now we will see that the static optimization, let's say that there is a utility function which is with the product x and y. So the it will be less than or equal to, right? So now let's say that if you have a maximization of utility uh, function, then what we will do is we will maximize the utility subject to certain constraints. In this case, Px is price of x is quantity, Py is price of y is quantity, and I is the total income. So in this case, what we do is we are arriving the optimum consumption x star and y star. Now in dynamic optimization, what we do is our objective is to maximize the lifetime utility by optimizing the consumption of x and y at each time period. So the decision variable is investment at each time period. Okay. So in static optimization, we like in the example as be shown here, the optimum consumption of x star and y star is obtained. However, here in this case, we have x1, x2, x3, and so on. y1, y2, y3, and so on. So here we have only x and y after the optimization. However, here for each time period t1, t2, t3 and so on, we will have different optimum levels. So this is the optimality, right? Now, the decision variable in this case is, let's take an example that investment at each period, right? So we are so it can be of any type, but in this case, let's say that the 5-year economy of a country is uh, to be um, improved from economic state 0 comma a, which is initial state of the economy, and t comma z, which is terminal state of the economy, and z is the capital stock at the terminal state, and a is the capital stock at initial state, right? Now, let's say that there is a path for the first year from A, there is a movement towards the B, and then towards the C, D, E, and then finally towards the point T, Z, final state. Okay. Now let's try to see few other points. Let's say that few other paths such as A, B, C, D, E, and then A, P, Q, R, S, and then final, and then A, X, Y, W, V, and Z, and A, M, N, O, P, Z. So these are different paths. Okay. Now, which path will the economy be selected? Okay. Now, let's say that the investment required for each of the path A to X, A to P, A to B, and A to M are given here. So we will see that we will choose the A to X path. However, there might be the case that the cost, let's say that between the 50 and 100, the the A to M with lesser investment will be chosen. However, not merely by seeing this myopic view of first year, we cannot do the investment, because in the second year, the investment differs very large from 200 to 30. So, by overall seeing the total cost from A to Z in each of the paths, we will try to see the optimum path which needs to be chosen for attaining the T, Z economy state. So now we will select a particular path that will minimize the total cost of investment to reach that have minimum cost of investment to reach Z from A. So the myopic vision is not chosen, but overall travel cost is considered here. So in this case, we are taking the time period as discrete time period. Okay. Now we will move towards the continuous time period. So let's take an example in which the time period is continuous and we have first state 0, A and final state 0 t, z, where t is my time. Then from each of the paths C1, C2, C4 and C3, which path will be chosen? So let's say that this straight line is my C4, then I will choose C4. Why? Because it is a straight line and others are curves. So the straight line will have shortest distance, right? So the cost will be minimum compared to other paths. So C4 is the least cost for achieving T, Z, as it is a straight line. So the C4 will be chosen in this case. So now we will learn about the important elements of dynamic optimization. So the important elements of dynamic optimization, first we should have an initial state which is denoted by 0, A, and terminal state which is denoted by T, Z. So next is there are different paths to achieve the terminal state, and there should be a decision variable. So in this example, we will be having the investment, how much investment we have to do at T1, T2, and so on, right? So if we do the 50, 100, 60, 10, we will have different values of tau or different economy state. So based on the minimum cost of travel, we will choose the path. So next is we should have an objective functional which we are trying to optimize. Now, in this case, we have said that the objective functional should be there, not a objective function. So why it is objective functional but not a objective function? So in static optimization, we have point-to-point mapping. So for each of the x comma y, there is a u, and we get the optimal x comma y, which gives the maximum u. So therefore, in this case, the objective function is used, right? So which is to maximize the utility u. So it is called objective function. However, in dynamic optimization, the mapping path z is sum of path or integral value of different paths. So we have different paths and the total of all will be our mapping path z. So we are mapping a path y1t, y2t, and so on to a real integral path, which is represented by v of yt, where yt indicates the paths and vyt is the integral value of path. So in this case, we have path as, let's say that A, B, C, D, A, M, N, O, and so on, right? So from here, we are getting the optimal path. So therefore, it is called dynamic optimization, not a static optimization. And this kind of objective, the objective function having this kind of mapping method can be then known as the function. So in this case, the objective is called functional. And v of yt, so here in this case, let's say that g of f of x, if we say, then it's a composite function where g is function of f and f is function of x. However, if I say v of yt, then it is not same as v is function of y and then it is a function of t. So this is not applicable in the second case. So v of yt is not a composite function. G of fx is a composite function. Okay. So it is not a composite function such as g of f of x. That is what we are trying to say here. So this this diagram shows us two paths, v1 and v2. So we will be a function with values having v1, v2, and so on. So these are the integral value of paths. So all the paths are integrated in the v. So now in the previous case, we have set 0 comma a and t comma z, right? So we feel that both the t and z are fixed in the final. So this is one of the case where both t and z are fixed. However, so in this t comma z is a fixed and we have different paths, right? So these are the different paths which we have and t comma z is fixed. So this is first type. However, there might be a case where either t or z or both may be variable in a dynamic optimization. So let's say that my terminal situation t comma z, then there are several alternatives. First one is t is fixed. That is that the time at which the economy have to attain is fixed, and we are obtaining various economy states z1, z2, z3, and so on. So the initial state is 0 comma a and these are my final states. Then our objective will be to choose the maximum z which is achieved at minimum cost. So the minimum investment cost and maximum Z is our objective in the first case. Now let's say that my Z is fixed. Then what will be my objective? So then in this case, the time at which this Z is obtained, T1, T2, T3. So minimum time will be our desirable value, right? So the objective is to achieve the terminal state of capital at minimum amount of time. So our Z is fixed, so we have to achieve it at a minimum time. Then there are a case where both T and Z are variable, so it is represented by function which is phi. Now if we summarize, then we can say that in an economy that begins with the initial capital stock and aims to reach a desirable terminal capital stock, the decision variable is the investment made in each period, that is 1 year. And our objective is to achieve the terminal capital stock at the minimum possible cost. So this kind of optimization will be called as dynamic optimization. And the key elements of dynamic optimization is first, the initial state and final state should be there, defining the starting and desired final condition, and then the decision variable. Uh, it can be investment, or in the static case, then the utility maximization was there, that is how to consume. However, let's say that let's take an example of resource extraction. So in this case, then optimal rate of extraction will be our uh, objective. Sorry, will be our decision variable, and objective will be function of optimal rate of extraction. So it might be like, let's say, barrels of oil or tons of corn. So how much to be extracted will be our decision variable. Or in the example which we have taken, the investment, how much to be invested at each period is our objective. Now, let's say that the objective functional. So unlike static optimization, where we have objective function, dynamic optimization uses the objective functional to map the different paths over the time, right? So optimization process, we will adjust the decision at each period based on market condition, and our objective is to minimize the total benefit by end of the time. So this is what we have taken as an example, where we our objective is to find the path where the maximum total benefit is extracted. Uh, so this is all for the introduction of resource economics and dynamic optimization. So we can conclude that the resource extraction not a function is not a function of one time, but it is time dependent from t is equals to 1 to the overall lifetime of a resource. So in this case, we will use dynamic optimization, and dynamic optimization have a set of paths, and you have to choose a path based on your objective and decision variable. So the decision variable can be investment, or it can be optimal rate of extraction, right? And our objective is, in the previous case, is to find the minimum uh, investment, right? Or or it might be to achieve the maximum economy state at minimum investment. And in the resource constant case, we can say that the objective will be to maximize the total benefit by the end of time, or total benefit from t is equals to 0 to the end of time horizon, while taking into consideration the rate of extraction from each time t is equals to 1 to t is equals to capital T, and we find the optimal rate of extraction at each of the time. In this, we will see some questions of week 9 practice questions. So first one says that the which of the following is a renewable resource? So the biological species are renewable resources which have regenerating capacity and which is naturally occurring resources, right? So the correct answer is B. Now, in the second question, for ordinary marketable goods, optimal rate of extraction is decided by the factor that price of good is equal to marginal cost of production of good. So the correct answer is second one. So in the third question, we are asked the augmented marginal cost. This is given by marginal cost of extraction plus marginal user cost, right? So augmented marginal cost, as we have discussed in this, will be equal to marginal user cost plus the marginal cost, right? So marginal cost of extraction and marginal user cost will be the correct answer. Now, the fourth question is which among the following statements are true with respect to dynamic optimization? So there should be an initial and terminal state. There are different paths to achieve terminal state. There should be a decision variable and there should be an objective functional which is to be maximized. So from all this, all of these are true with respect to dynamic optimization. So they all of the above are true is the right answer. So now we are asked which of the following is not an example of backstop. So all of the options given here are example of backstop. So the correct answer is last one, none of the above. And in the sixth question, we are asked which among the following is true with respect to backstop. So marginal cost of extraction of backstop determines the price part of the existing resource at time t. Also, this sets the upper limit on the price of existing resource at time period t. So here we have discussed we have derived the value of here in this we have derived the value of price as a function of value of price as a function of wait a minute, I'll find the slide. Okay, so here we can see that here we are now we have backstop. From here we have derived the price as a function of MCB. So this marginal cost of backstop is one of the factor which determines the path of existing resource at time t, and it also determines the at the upper limit of the price of existing resource at time period t. So these two options are correct in this case. So this is all for the practice question, and moving on uh, to the assignment question, we are asked renewable natural resources are basically naturally occurring resources with its regenerating capacity should be there within the economically feasible time horizon. So the correct answer is option D. Moving on. So regenerating capacity within the uneconomically time horizon should be there for naturally occurring resources. In the second question, we are asked, we cannot apply marginal cost of pricing in the case of non-renewable resources because, so the correct answer is that the extraction of non-renewable resources have some opportunity cost. So this opportunity cost is not considered when we are equating the price with the marginal cost. So this marginal cost pricing is not applicable in the case of non-renewable resources with the reason that extraction of renewable resources have some opportunity cost also, so which needs to be considered. Now, option number 3, reinvestment in revenue generated from extraction of non-renewable resource depend on, first one is rate of extraction of renewable resources, second one is present stock of renewable resources, and third one is rate of technological advancement. So the correct answer is all of the above, right? So the reinvestment from the revenue generated from non-renewable resources will be high with higher rate of extraction, and it will be lower when present stock is high, and it will be lower when the rate of technological advances is faster. So all these three are the reasons, or all these three are the dependency on the reinvestment. So therefore the correct answer is all. So now we are asked the initial marginal cost of extraction of backstop is, it will be higher than the marginal cost of extraction of existing non-renewable resources. So the correct answer is option C. Now, in the fifth question, we are asked which of the following rules determines the optimal extraction of ordinary marketable goods. So for ordinary marketable goods, the price of good will be always equal to marginal cost of production of good. So marginal cost of production of good is dP by dQ. So when P is equals to dP by dQ, then this condition will determine the price. So now in the sixth question, we have already discussed previously. The correct answer is A and B. And the seventh question, the most socially and economically profitable extraction of a non-renewable resources is along the marginal resource trend must grow at the rate of interest or discount. So this law is given by Hotelling rule. So the correct answer is Hotelling rule, and we have discussed about that. The Hotelling rule gives us that the change in the present uh, change in the rent will give us R value, and this growth of uh, resource rent will be equal to R value, and this R is dependent on person to person, and price for the future is expected price. And here we are given price Pt at time t, P1 at time 0, P1, P, P0 at time 0 and Pt at time t, and we are given discount rate. So we have to find the expression for price paths. So it is given by Pt is equals to marginal cost plus resource rent multiplied by 1 plus r to the power t. So we have derived this expression in the previous part. Now marginal resource rent is given by price minus the marginal cost of extraction, and in the last question we are asked what will be the growth of marginal resource rent. So it will be resource rent at time t minus resource rent at time 0 divided by resource rent at time 0. So the correct answer is option B, that is P1 minus MCE minus P0 minus MCE divided by P0 minus MCE. So with this we will end today's session. So thank you so much for joining.